Our last section in this module and in this chapter is 24.8, where we look at the normal distribution. You're already familiar with this distribution, the famous bell-shaped curve or Gaussian distribution. It describes continuous random variables that might lie anywhere from negative infinity to positive infinity, but we have parameters mu and sigma, which correspond to the mean and standard deviation. While this occurs all the time in natural situations, the PDF is actually rather complicated to calculate. It's given here. I've, we never do this. We never calculate the PDF. It's not really that interesting to us. Um, it turns out we're a lot more interested in the cumulative distribution function because that's the one that we can get probabilities from. But the equation is complicated to the point where we can't write down the equation in closed form. It's not analytically solvable. So what we end up having to do is to use tabulated or approximate results to estimate the CDF or cumulative distribution function. The mean and variance of this distribution are straightforward in that they are the parameters that we started with. The mean is mu and the variance is sigma squared. Here are a couple different normal distributions shown on the upper two curves. The left one, upper left, has a mean of 35 and a standard deviation of 4.2. The one on the upper right has a mean of 35, but now a standard deviation of 7.2. So you see a lot more spread in the one on the upper right. On the bottom left and bottom right, you see the CDF, the corresponding cumulative distribution function for each. Notice that the CDF has its peak become most steep at the mean of the distribution. If you compare the curves on the bottom left to the bottom right, you can see that the spread is wider on the one on the bottom right. It takes more time for the curve to go from 0 to 1, or a larger distance for it to go from 0 to 1 on the bottom right. Notice also that the value of f of x at the mean is equal to 0.5, because half the distribution lies to the left of it at that point and half to the right. Another thing to note is if you compare the peak values in the upper left to the upper right, because the spread is wider on the right, but the area under the curve is the same, the peak on the upper right has to be lower than the peak on the upper left curve. We actually need one more normal distribution, and that's a special one. It's a distribution that has a mean of 0 and a standard deviation of 1. We find this useful because we can stretch this normal distribution and shift it to match any other normal distribution. So this is the one we actually tabulate. And its PDF is written in that form there, and it's valid for all values of x from minus infinity to positive infinity, and the corresponding CDF is written as capital phi of x and is defined as the integral from minus infinity to x of the PDF. It's this capital phi of x that's tabulated. So it's this CDF that we have tabulated, and you have one of these tables in the appendix of your textbook. What does the standard normal distribution look like? Well, here it is, and you see in blue the PDF, and in red the CDF, and it's the red one, or CDF, that's tabulated that we use in order to find probabilities. We tabulate that standard normal distribution, but we can shift it and stretch it to match any other normal distribution with this transformation. We can take our variable space, or our variable x, and its mean and variance, and convert it to the standard normal using this equation. Take your x minus its mean, divide by your standard deviation, and you'll have transformed to the standard normal variable space. And now the mean of z is 0, and the standard deviation of z is 1. So you can convert from your variable space to the standard normal space with this transformation. So you'll probably want to just memorize this. Here is the tabled CDF, and you can't really read it, but this is, I include it so that you can see what your table A7 looks like. But now let me focus in on the top half. So here's the top half of that distribution. And notice that we can, for any value of z, we can look up the capital phi of z and get the probability that you have that value of z or lower. This is really only half the CDF because we haven't tabulated any values where z is negative. If you want to get a value CDF when the z is negative, then you have to use the equation that's in the upper right of this table. And I'm glad that that equation is on the table, so I'll just include that with what you get when you take exam 2 in the final exam. Notice that if you have a negative z, you can get the capital phi of that negative z by taking 1 minus the capital phi of the positive version of your z. So if you want, for example, I'll show you how you can look up that if you have want to find the value for a negative 2.17. What you would do is use this chart to look up the value for positive 2.17, and we look up and find that we have a probability of 0.9850 for positive 2.7. But because we wanted a negative 2.17, we would take 1 minus 0.9850, or 0.0150 would be our answer. 0.0150 would be our result for the capital phi of a minus 2.17. This is the top half of the curve, the table, and the bottom. Here's the bottom half of the same table where I need to split the table up into two different slides so that I can use that in examples. Some other features of the standard normal, the normal distribution, come from a good understanding of how the standard deviation operates. When you look within one standard deviation of the mean of your normal distribution, you'll have included about 68% of the population of your distribution. When you expand your interest to the portion of the population that lies within two standard deviations, you get a much larger lump of the entire population. About 95.5% of the entire population, I usually remember this as about 95% of the population, lies within two standard deviations of the mean, and about 3 standard deviations within the mean includes about 99.7% of the population. So you only have about 0.3% of the population lying more than 3 standard deviations away from the mean. It's a good way, some rules of thumb to help understand the normal distribution a little better. There's another type of task that we look at with the normal distribution. We might be willing to tolerate or might be willing to design for the majority of the distribution, but recognize that we're not going to be able to economically accommodate some of the tails. So we might want to know the for example, what is the value of z such that only 5% will exceed it? Say we want to be able to accept 95% of cases, but recognize that 5% of cases are just going to be too expensive for us to be able to accommodate. In that case, we would want the z alpha that would be associated with that alpha of 5%, and would want to find that value of z that we need to design for. Graphically, what we want then is to recognize, okay, there's a portion of the population I've shown here in green that we're not going to be able to accommodate that case. So what we want to find is the z associated with that population, or that fraction of the population. So we are going to use the table in reverse, where we have the phi of z, and what we want to get is the z associated with it. Another related case that we need to consider is when both tails are just too difficult for us to be able to accommodate. Or so what we do in that case is recognize that we might have the upper and the lower tails just simply beyond our ability, and we want to design to consider the majority of the population that lies within the limits, not in those tails. In this case, what we would want is to find the z alpha over 2 associated with that alpha over 2%. So in our 5% case, we recognize that there's going to be 2.5% in the upper tail and 2.5% in the lower tail that we're just simply not going to be able to accommodate. Graphically, what we want then is the z alpha over 2 associated with this case, with the two-sided case. It's also useful to notice that linear functions of a normally distributed random variable are easy for us to accommodate. If we have some random variable x that has a mean of mu and a standard deviation of sigma, and we have a and b are constants in a linear function such as y is equal to ax plus b, if we know that x is normally distributed, then we'd know that y is also normally distributed. Further, we can get that normal distribution because we know that it will have a mean, that y will be distributed with a mean of a times mu plus b, and it will have a standard deviation of the absolute value of a times sigma. Notice that you have to remember to use that absolute value of a, because if your linear function shifts your variable to the right or to the left, isn't going to alter the amount to which it um, has isn't going to change the amount of its spread. So the standard deviation is always positive, so we have to remember to use the positive or the absolute value of a. It's also very useful to use the normal distribution to approximate the binomial distribution. This can be valid and save us a lot of work when we're dealing with a large number of cases from the binomial distribution. It's a reasonable approximation whenever both n times p is greater than 5 and n times 1 minus p is also greater than 5. And we use this because calculating the CDF of the binomial distribution is very tedious. And we need to deal with the complexity of the challenge of the fact that the binomial distribution is designed for discrete variables, whereas the normal distribution is associated with a continuous variable. And we're going to have always the case of, do you want the lump or do you not want the lump? I'll use an example of, suppose you have the probability you're making screws and you ship screws in a box of 200, and you want to know whether the chance that you might get more than 10 defective screws in that box of 200 is beyond a certain threshold. So you might want to say, what's the probability that 10 or more screws are defective? Or you might say, what is the probability that more than 10 screws are defective? In one case, you wanted the lump at 10. In the other case, you didn't want that lump at 10. So 10 or more, you want the lump. More than 10, you don't want the lump. In one case, you'd want to actually start your normal approximation at 9.5 and include the lump. And in the other case, you want to start your normal distribution at 10.5 and not include the lump. And I hope that explanation helps, because the mathematical equation for it can look a little overwhelming. That's why I explained it first. When you actually look at what that means, what it means is that you're going to be calculating the probability, the CDF, then either including that lump or not including that lump. And so that's why the two different versions of the application have either an x plus 0.5 or x minus 0.5. And I don't want to overwhelm you with this. This will be easier once we get to application. So we'll wait for some example problems to get into the use of this equation. Lastly, I wanted to mention that the central limit theorem, which we're really going to get into in the next chapter, is explains why the normal distribution comes up so often in nature. Again, this central limit theorem we'll get to in the next chapter.